Good morning, students. I hope all of you are safe at home. And yesterday, I think that you have gone through the video. I hope that all of you have understood and did the calculation part for the PK experiment. Today, I am going to demonstrate to you the second instrumentation experiment, that is estimation of FAS potentiometrically using standard potassium dichromate solution. One request to all the students, when you are listening to the video, please keep your manual with you so that you will understand it very well. Okay? So we are determining estimation of amount of FAS. What is FAS? FAS is nothing but ferrous ammonium sulfate. So it is a double salt of ferrous sulfate and ammonium sulfate. If you see the formula of FAS, ferrous sulfate FeSO4, ammonium sulfate NH4 twice SO4, and it is hydrated with 6 water molecules. So it is a double salt of ferrous sulfate and ammonium sulfate. And the other name of FAS is more salt. Okay, now we are going to estimate the amount of FAS present in the given FAS solution using standard potassium dichromate. We are using dichromate solution K2Cr2O7. So when we say reaction between FAS and dichromate, those reactions are called redox reactions. That means as one gets oxidized and the other reagent gets reduced. So it is a type of redox reaction. And now before we are proceeding to the experiment, you have to understand what is a potentiometric titration. So potentiometric titration is nothing but we are determining the equivalence point of a redox reaction using a potentiometer by measuring the EMF of the solution. That means in this reaction, FAS reacting with potassium dichromate, where in FAS the iron is in +2 oxidation state, which is getting oxidized from +2 to +3, and the potassium dichromate, where the chromium is in +6 oxidation state, getting reduced to +3 oxidation state. So this redox reaction, for this redox reaction, we are going to determine the equivalence point by measuring the EMF of the solution using a potentiometer. So you have to know again one more word, EMF. EMF is nothing but E cathode minus E anode. All of you know, you have studied Nernst equation. Because this experiment works on the principle of Nernst equation, E is equal to E naught plus 0.591 by n log of Mn plus. You have derived the Nernst equation and you have studied the applications of Nernst equation, which is very important also. So based on that principle, this potentiometer works. Okay. Now coming to the explanation of this instrument, this is the potentiometer, and this potentiometer is connected with two electrodes. One is a calomel electrode which is called as a secondary reference electrode, and another electrode is the platinum electrode which is called as indicator electrode. Please try to understand here. The potentiometer is connected to two electrodes. One is calomel, which is a secondary reference electrode, and this is platinum electrode, which is an indicator electrode. All of you know what is a reference electrode, because whose potential can be determined by using a standard hydrogen electrode. And next you have to know what is an indicator electrode. This electrode is the electrode whose potential depends on the concentration of the ion what we are going to determine in the titration. Okay, this is platinum electrode and this is calomel electrode. So now we will start doing the experiment. Before we are doing the experiment, first we have to wash these two electrodes carefully with the distilled water on all sides. And now take out the beaker containing distilled water. Now you are taking a beaker containing FAS solution. ferrous ammonium sulfate solution. No need to add water. Dip the 2 electrodes in the FeS solution, and now you take a test tube and take a reagent bottle containing sulfuric acid and take sulfuric acid into this one test tube and add the one test tube of sulfuric acid into the FeS solution. Please remember, this is very important step of the reaction. If you won't add sulfuric acid, you will not get the accurate results. I'll tell you why later. So it is very important that you have to add one test tube of sulfuric acid to the given FeS solution before we are doing the titration. Okay. Now after adding sulfuric acid, now we have to shake the solution well once and measure the EMF of the solution. Now it is showing 330 EMF. Okay. Now we are taking a burette, which is a microburette. Again, the capacity of the burette is 25 ml. Filled with potassium dichromate. You can see the orange color. It's potassium dichromate, where the chromium is in +6 oxidation state. And putting downwards, see that the nozzle should be inside the beaker. Now the instrument is ready for doing the experiment. Okay. Now in the manual book, we will take the tabular column to note down the values in the tabular column. Without adding potassium dichromate, the FeS solution is showing a potential EMF of 335. We have noted down. Now we have to add, like yesterday's experiment, the potassium dichromate in 0.5 ml increments, only 0.5 ml increments, and after addition of 0.5 ml increments, you have to shake the solution well. Redox reaction is occurring where iron is getting oxidized and the chromium is getting reduced. And now we have to note down the potential of this EMF is 388. It will increase when you are adding the potassium dichromate. Now again you are going to add again 0.5 ml of dichromate. So you can observe the color change of the solution here. The solution is slowly changing into green color. It is an indication that the redox reaction is occurring. So after shaking the solution, now you have to note down the constant EMF of the solution. It is 406. Now again we are going to add 0.5 ml, that is from 1 to 1.5 ml of potassium dichromate. Again shaking the solution. See the color intensity of the green color is increasing. And now again you will be noting down the EMF 423. And now again you have to add 0.5 ml, it is from 1.5 to 2 ml of dichromate solution. We will be shaking the solution. Should be very careful with the electrodes what we are using inside while we are shaking. Now you will be getting 436. You have to note down. Now again we will be adding the dichromate from 2 to 2.5. Again shaking. And noting down the EMF of the solution. It is 450. Now again we have to add 0.5 ml, that is from 2.5 to 3. Again shaking the solution. It is 458. Again we will be adding 0.5 ml, that is from 3 to 3.5 ml, and shaking the solution. See, the color intensity is increasing, it's becoming thick green now, and now it is 471. It is increasing. 3.5 to 4 I am adding. Again shaking. Now the EMF of the solution is 481. Now again I am adding 0.5 ml, that is from 4 to 4.5. Again shaking. If you won't shake the solution, otherwise the redox reaction will not occur. Now the potential is increasing drastically from 400 to 500. That means we are reaching the equivalence point. It is an indication that the equivalence point is reaching. So now the EMF is 502. Now I am adding from 4.5 to 5. Now see that potential is increasing. It takes time for 424, 25, 26, 28, 29, like that it is increasing. 536. Now, dear students, now we are going to do the calculation part of the values what we have noted down for the potentiometry experiment. Okay, we have noted down the EMF from 0 to 6.5, addition of potassium dichromate, and we have observed a sudden change in the EMF from 500 to 900 between 5 to 5.5. Okay, now for doing the calculation part, again we have to fill this tabular column. Okay, to fill this tabular column, now again for first you have to take for the 0 reading, delta E 0, delta V 0, delta E by delta V 0. Okay, now for 0.5 ml of dichromate, the delta E, again you take the difference of the previous reading and the present reading. Note down the value. And delta V, always we are adding in 5 ml increments, so it is always 0.5 ml. So note down it as 0.5. So delta V always 0.5. And delta E is the difference of the EMF between the present reading and previous reading. You take like that and fill this column completely. And then after filling the delta E, delta V you know 0.5, then you calculate delta E by delta V and see that you have to calculate up to for 6.5 ml. So after doing this calculation part, now we have to plot the graph. So for plotting the graph, we have to take volume of potassium dichromate on x-axis, delta E by delta V on y-axis. So here when we are taking on x-axis dichromate volume, you take it as 0.5, each unit 0.5. So 0.5, 1, 1.5, 2, 2.5 like this. And on y-axis, you have to take each unit of 50. 50, 100, 150, 200, 250, 300, 350, like that you take for delta E by delta V on y-axis. For your values of delta E by delta V, against the volume of dichromate added, you indicate all the points in your graph and draw a smooth curve using covering all the points. Again you will observe a sudden jump in the EMF. From that point, you draw a straight line onto the x-axis. So when you draw a straight line onto the x-axis, this point corresponds to the equivalence point. I told you the difference of end point and equivalence point. So here in instrumentation experiments, we will call it as the equivalence point instead of end point. So you will be noting down the equivalence point for this experiment. That is, the equivalence point is the point exactly where the reaction is completed. Okay, you will note down whether it is 4.5 or 5.5 or 6.5, whatever you are getting, you please note down the equivalence point. There is only one graph for this experiment for the determination of equivalence point. From the equivalence point, now we have to do the calculation part. Okay, now coming to your manual book, after the tabular column, you are having the calculation part. So in the calculation part, from the graph, volume of dichromate at equivalence point. So whatever you are getting, whether it is 4.4 or 5 or 5.5 or 6.5, whatever you are getting, you make a note of the equivalence point here. And then volume of FAS used is 25. All of you note down. It's a 25 cm cube, which I'm giving you. Next, normality of dichromate. We are using a standard dichromate solution. Its normality is 0.5 normal. Okay, note down that value also. So from the normality of dichromate and volume of FAS and volume of dichromate, you find out the normality of FAS. So you will be finding out by substituting all these values, finding out the normality of FAS. So first step is finding out the normality of FAS. From the normality of FAS, you are finding out weight of FAS per liter. How will you get is, you multiply the normality with the equivalent weight of FAS. You have to remember this equivalence weight. The equivalence weight is 392. So if you multiply the normality with the equivalent weight, you will get amount in grams. Per liter you will get, but you have to calculate for 25 ml taken. So weight of FAS per 25 centimeter cube is equal to whatever the weight you are getting here into 25 divided by 1000. If you do, you will get what is the amount of FAS present in the 1000 ml solution, and normality of FAS also you will get. So this is the experiment. Potentiometrically we are determining the amount of FAS present in the given solution. I think all of you have understood. Take down the readings. I will send you the readings also. From the readings, you fill the tabular column. From the tabular column, you plot the graph. From the graph, you substitute the values in the calculation part and do calculation. And after doing the calculation, you start writing the record. And after coming to the college back, once you can do this experiment with your hand. Thank you.